Hi all, today we discuss chapter 4 surfaces. First we have a definition. A surface of dimension n or an n surface in Rn plus 1 is a non-empty subset S of Rn plus 1 of the form S equal to F inverse C, where F from U to R, U is an open subset of Rn plus 1. That F should be smooth function with the property that del F of P not equal to 0 for all P belongs to S. That means first of all that S should be a level set of some function, some smooth function, and every point of that S should be a regular point. Del F P not equal to 0 means that point should be a regular point. So for a surface, we need to take two quantities, an open set and a smooth function defining on that open set. Then we can construct a surface using F inverse C. So the first remark is, when you consider one surface, then one surface is also called a plane curve. Okay, one surface means we need to construct a function from smooth function from our R2 to R, or a subset of R2 to R. I write that function as f of xy is equal to x square plus y square. So if we consider f inverse of some 1, then that will give set of all xy such that x square plus y square is equal to 1. So this is an example of one surface. This is nothing but our unit circle in R2. Okay? So this is what we called a one surface. In order to verify that this is a one surface, we need to verify that del f of p not equal to 0. So first of all, you need to check del f of p from this f of xy. Del f of p is nothing but at the point p we assign dou f by dou x, that is 2x, and dou f by dou y, that is 2y. So this constitute a vector del of p. This del of p is non-zero means this part should be non-zero. Okay, if this is 0, then you can get x equal to 0 and y equal to 0. Then x square plus y square never be 1. So we can say that that xy does not belong to this set. So in order to be an element of this set, that x and y should be non-zero quantities. Any one of them should be non-zero quantity, and we have x square plus y square is equal to 1. So we can say that this never be 0, this del f of p, this is the definition for the value of del f of p. So this del f of p never be 0 for all points of this f inverse 1. So we can say that this is a one surface. In this chapter, later onwards, we will discuss the examples for one surface, two surface, etc. So this one surface is also called a plane curve. And two surface in R3 is usually called simply a surface. Okay, an n surface in Rn plus 1 is often called a hypersurface, especially when n greater than 2. These are the three remarks on the definition of the surface. Next we have surface and tangent space. Each n surface S has at each point P belongs to S a tangent space which is an n-dimensional vector space of the space of all vectors at P. That means this Rpn plus 1 is called all vectors at P. Okay, this is what we called tangent space at a surface. We have already discussed the tangent space at a point in the level set. Okay, now if we consider a surface like this, if we consider a surface like this, if you consider a point P here, then consider all the tangent vectors at P. Okay, you can construct so many tangent vectors at P by taking the parameterized curves passing on this P. So this is what we called the tangent space at P. That is what we call set of all vectors at P. So this is what we call tangent space, which is n-dimensional vector space, vector subspace of the space Rpn plus 1. So likewise, the tangent space at a point P in the level set, you can construct the tangent space of a point P in on a surface. Okay, so these are the remarks. The tangent space at the point P on the surface S will be denoted by SP. This is the symbol for tangent space of a surface. This denotes set of all tangent vectors at P on S. If f is any smooth function such that S equal to f inverse of C for some C belongs to R and del f p not equal to 0 for all p belongs to S, then SP may also be described as del f of p perpendicular. Okay, we have already discussed this result in case of level sets. So the same result holds for this tangent space at P where del f p not equal to 0. Now we have examples. We have a number of examples in this chapter. First one is example 4.1. In example 4.1, we have f from Rn plus 1 to Rb defined by f of x1 plus x1 comma x2 plus etc. xn plus 1 equal to sum of the squares of these coordinates. So that is what, then if you define s equal to f inverse 1, then that is called, that should be an end surface in Rn plus 1 with del f p not equal to 0 for all p belongs to S where del f p is equal to this one. Okay, so the f inverse, precise elements of this f inverse 1 is there is set of all x1 x2 etc xn plus 1 such that x1 square plus etc xn plus 1 square. Okay, this is what we call this surface, and this surface is called a unit n sphere in Rn plus 1. Okay, so this is always a subset of Rn plus 1, and this is called n surface instead of n plus 1 surface. This is n surface because there are several reasons for defining this as an n surface, because at every point P the tangent space is homomorphic to Rn, or you can say that this sphere in Rn plus 1 is a n manifold and so on. So in advanced studies we have so many reasons to define this as an n surface instead of n plus 1 surface. Okay, even though this is this resides in Rn plus 1. Okay, then what is the remarks? For a vector p comma v belongs to Rn plus 1 to be 0, it is only necessary that v equal to 0. Okay, this is the idea I just mentioned above. When you consider a vector p, this vector is said to be 0. We need to set this vector part is 0. Okay, but then we call it as a 0 vector at the point P. So this P stands for to represent this is a vector at P. That is the meaning of this P. Okay, so in order to get a 0 vector at P, we need to use the notation P comma 0. This is enough. Now del f p equal to 0 means this vector part is 0. This vector part is 0 means each coordinates should be 0. So if each coordinate is 0 means that never be an element of S, because in the surface we have sum of the squares of this is equal to 1. So we can never say that this is an element of S. So for every element of S we have this vector part never be 0, hence this del of p is non-zero for every p belongs to S, and hence this is an n surface. Now we have another example, example 4.2. If you choose a vector in Rn plus 1 as this is a point in Rn plus 1, not a vector, a1, a2, etc. n plus 1, and b belongs to R, the n plane. Okay, you can define this as an n plane. This is an n plane. A1 x1 plus etc plus an plus 1 xn plus 1 equal to b. This is the level set f inverse b of the function this a1 x1 plus etc. Okay, so this is a very trivial surface. When you consider del f, then you can get del f as at the point p, that is this is the point p. At any point we assign this vector. This never be 0 because we have chosen this a1, a2, etc. n plus 1 as non-zero. So this del f be not equal to 0 for every point in this level set. Okay, so this is what we call an n plane. Okay, this is the name of this. Then what are some remarks also there? A one plane is called a line. Okay, if you set this n is equal to 1, then you can get that as a1 x1 plus a2 x2 equal to some value, uh, some b. Then this is what we call a line. Okay, this is an equation of a line in R2. So this one plane is called a line, and two plane is a plane itself, that resides in R3. So when you consider two plane when n is equal to 2, then that will this reduces to a1 x1 plus a2 x2 plus a3 x3 equal to b. This will give a plane in R3. Okay. Now, an n-plane for n greater than 2 is sometimes called hyperplane, and these are the names we need to remember in the further discussions. Two different values of b with the same value of a1, a2, etc. n plus 1 define parallel planes. That means if you once you define a1 x1 plus a2 x2 plus a2 x2 is equal to some 1 first, then you define a1 x1 plus a2 x2 using the same values of a1 and a2. You can define as a one plane with some other value of b, so you can get the two parallel straight lines. Okay, so these are called parallel and planes. Okay, in general, if in this case we have another, we can get a plane like this. So for different values of b, we have another value of b, you can get this type of planes. These planes are parallel planes. So for the same values of this vector and different values of b, we can get the n planes. Now we have surface of revolution. This is a nice example. When you consider a plane curve, this is one thing you should remember is this surface of revolution is defined only for case of a curve C in R2. Okay, that means the surface of revolution resides in R3. We will define this surface of revolution in this manner. That should be an element of the subset of R3 anyway. So if in order to define this surface of revolution, we start with a plane curve in R2. Okay, which lies above the x-axis. So if we start with a plane curve, this is x and this is y, and we choose a plane curve in R2. Okay, now thus C is equal to F inverse C for some F from U to R with del F P not equal to 0 for all P belongs to C. Because C is a curve with these properties, then if you choose U is contained in the upper half plane, x2 greater than 0. I call this as x1 and this is x2. Okay, so we consider a subset. Here I consider a subset U, and this plane curve F inverse C is always a subset of this U. Define using this curve. Okay, using this curve, define and map surface S is equal to G inverse C. Okay, what is G inverse C? G inverse C is this C is same as this one, F inverse C. So using that C, we define S equal to G inverse C, defined by that surface that G is a function from U cross R to R, and in fact this U is a subset of R square, right? So the domain of G is always a open set in R3. Okay, so this G is a function from R3 to R. Now consider G inverse C. So that is always a subset of R3, defined by G of x1 x2 x3 is equal to f of x1 comma x2 square plus x3 square whole raised to 1 by 2 is equal to 1 by 2. So this is what we call G, the function G. So what is G inverse C? That is the next step. To define G inverse C, you need to define set of all x1, x2, x3 such that this G of x1, x2, x3 is equal to C. That means this value is equal to C. F of x1, x2 square plus x3 square whole raised to 1 by 2 equal to C. This is the surface G inverse C. Okay, so to understand this surface, we set a point P is equal to AB in C. AB in C means this C is the plane curve. This is the small c, and if you fix a point P, A comma B in this plane curve, you can say that this P generates a circle of points of S, namely the circle in the plane x1 equal to A, and this, that means if we consider this point AB, we can say that this x1 equal to A, and this part is equal to x2 square plus x3 square whole raised to 1 by 2 equal to B. Okay, so that is the square is equal to x2 square plus x3 square. So this is actually whole raised to 1 by 2. Okay, so that will be equal to x2 square plus x3 square is equal to B square. So that generates a circle like this. Okay, so this is our B. Okay, so at each point corresponds a circle here. So this will be our surface of revolution in R3. Okay, this is the set G inverse C. Okay, so corresponding to each point AB belongs to C, we can construct a circle like this in G inverse C. Okay, when you consider this f of x1 comma this quantity is equal to C, means this is a value Z, so that means this A coincides with x1 and B coincides with this one. Okay, so you can get it as either this whole raised 1 by 2 is equal to B, or this is equal to B square. Okay, so this is what we call a surface of revolution. Now we have graph and surfaces. A graph as an end surface. Okay, if you have a function f from u to b r be a smooth function on u, and u is open in Rn plus 1, then graph of f. We have already defined this graph. Graph as x1, x2, etc. xn plus 1 belongs to Rn plus 1 such that the last coordinate should be equal to f of the other n plus 1 minus 1 coordinates. So this is the definition of the graph. So this graph can be considered as, or if you define s equal to g inverse 0 in Rn plus 1 such that g of x1, x2, etc. xn plus 1 equal to this value. Okay, now this g is a function from you can say that this is a function from Rn plus 1 to this R. Okay, so then G inverse 0. What is G inverse 0? G inverse 0 coincides with this set. Okay, G inverse 0 is set of all x1, x2, etc. xn plus 1 such that this quantity is equal to 0. This quantity equal to 0 means xn plus 1 is equal to this one. So any graph can be considered as a surface or level end surface of some function. Okay, so here we have del G of this is equal to this one. At the point x1, xn plus 1, we define these vectors. Okay, this is the value of del G. Okay, then del G not equal to 0 because the last quantity is 1, that is not equal to 0. So this vector part never be 0 in any manner. Okay, since the last quantity is nothing but the derivative of this xn plus 1 with xn plus 1, so that will be 1. So this is always non-zero quantity.